Hello everyone, welcome back to my channel, Predicting the Future. Today we're going to talk about some serious mathematics, and that's the beauty of mathematics especially in probability theories. So we're going to talk about some graduate level of probability theories, and I will try to make it not that analytical, but more easier to understand. But still, we want to cover most of the topics in probability theories in here, step by step. So the first thing we want to talk about is that whenever we talk about a probability, there must be some outputs and there's some samples. There's possible all the possible outputs, and there's possible all the possible events that could happen in any experiment. So for that we are talking about probability space, and there are two elements in probability space. Here, there's three elements in probability space. They are the sample space where we use omega, which is all the possible outputs of a certain random variable, and F, we call it a sigma field or sigma algebra, which is all the possible events that could happen. And P is called a probability measure. So those are the fundamental three elements of the modern probability theory. So let's first about, so the sample space is easier to understand, but what is a sigma field? A sigma field, by definition, there's two properties that defines a sigma field. The first thing is that suppose A belongs to the sigma field, which is a set of collections F, then the A complement also is in this sigma field. Think about flipping coin. If tail is possible, then if head is possible, then tail is definitely possible. One of the events that we could observe. The second property is if a series of AI, which belongs to the sigma field F, which is a countable sequence of sets, then the union of those sets also belongs to F. So these two properties defines what is called sigma field, which is a collection of subsets of the sample space. Each collection is a possible event. And so that's sigma field. So what is a probability measure? So a probability measure, we know that a probability, if we take all the possible samples, we use P to measure all the possible samples, then that's has a probability 1. So that's everything is possible happening in this sample space. So P omega is 1, and that is the maximum value of P, right? But P is actually a function, and in mathematics, P is very highly related to integral calculus. People in the fresh year of university, we're going to learn about Riemann. We learn about Riemann integral, but Riemann integral have some problems. In some of the cases, it's not possible to do Riemann integral. So mathematicians come up with a better way of doing integration, which comes down to how we define the dx in a better way. So dx, we know it's the tiny small increment of x which is how we split the x-axis to a smaller and take the limit which will be the integral of the function. But sometimes it's not possible. For example, if we're gonna look at a function that is 1 on irrational numbers and 0 on rational numbers, then no matter how small we take the dx to be, how small dx is, the f of that dx, any value within that dx, we always have 0 and 1. So there's no way we can do the Riemann integral using the dx. So mathematicians come up with another way of concept of how we measure distance or measure the size of a set. Think about dx. It's a set. It's an interval. It's a set. And that I don't want to go too deep of that, but dx can be sort of a way of measuring size of a set, and we call it a measure. So we are measuring something. So there's, in mathematics, there's a measure theory, which is a huge topic, and it's the foundations of the modern mathematical and analysis. So let's talk about some basics of what is a measure. So a measure is just a function. It has two properties here. The first one, if a belongs to a sigma field, it's an element in a sigma field, then mu a is greater than or equal to mu null, which is empty set, which is equal to 0. The second property of a measure is if AI is a series of sets belongs to a sigma field F, is a sequence of disjoint countable sets, then the mu of the union of AI is equal to the summation of the mu of each AI. So they are disjoint sets. So the measure of the union of those disjoint sets is just a sum of the measure of each disjoint sets. So this is the two properties defines what defines a measure function. And a probability measure is a measure that has these two properties plus a measure of the whole space equal to 1. So mu doesn't have to be when mu is measuring the whole space, doesn't have to be 1. Right? So it could be infinity, it could be any number. But for probability, then this measure of the whole space is 1, and that defines a probability measure. Another example of probability measure is think about conditional probabilities. When we do conditional probability, so measure could be any possible. There's many measure functions. And conditional probability is another very interesting measure, which is basically by conditioning on a specific event, it itself becomes a new probability measure. So I'll start from here, and then we're gonna come back all those topics in the future. So the next thing we want to talk about is what are the properties of probability measure. So monotonicity, which is if a set A is a subset of B, then probability B minus A is just probability B minus probability A, which is greater than or equal to 0. Those are very basic things I'm gonna just go through very quickly. So sub-additivity, if A is a subset of a union of AN, then the probability of A is less than or equal to the summation of probability of AN. Continuity from below, if AI is set that increases and converges to a set A, then the probability of AI converges to probability of A. Similarly, continuity from above, so AI is a decreasing set to a set A, then probability of AI converges to probability A. So I believe everyone already knows those topics, but all those things can be explained in another way. Instead of using Riemann integrals, those are the same in probability in measure in in uh, in measure series. So another thing is sigma field. Here, if we look at this one, a sigma field of a collection set A, this symbol we're gonna see very often. This symbol means this is the smallest sigma field generated by A, by the collection, a set of collections A. The existence of this smallest sigma field is, just think about if this let's say if I is as a series of sigma fields that contains this subset subcollection A, then if we take the intersection of all those sets, which is actually this itself, the intersection of all those sigma fields Fi is actually a sigma field, which can be easily proved. And this is actually the smallest sigma field. Okay, so that's that. So just remember, this is very important. We're gonna see it very often in the future lectures. So next thing I have to introduce. I'm sorry, but this is very crucial. We don't have to go very deep of the underlying proofs of all those things, but we have to know. We have to have a concept what they are, and that's the foundations of the modern probability theory. Sorry. So next topics is about Borel sets. So let's say R is a real line, then the set B, I use R as well, but yeah. So the Borel set is the smallest sigma field. The Borel set is the smallest sigma field containing the open sets. You can think also, you can similarly, Borel set is actually generated by open intervals of, let's say, AB. So the Borel set is the smallest sigma field containing open sets. Equivalently, I would say equivalently, is the smallest sigma field. It's a sigma field generated by open intervals. And so that's the Borel set. Think about open interval from A to B, or half open interval A to B, or closed intervals. They all belongs to this Borel set. And lambda. So we're gonna talk about Lebesgue measure, lambda, which is the commonly used symbol for Lebesgue measure. So lambda is a measure function. It's a measure. It's a measure on Borel sets, and it's the only measure that if we measure that on a interval A and B, half open, or open or closed, doesn't matter, and that equals to B minus A. It sounds silly because that's right. We know it's an interval, so the length is B minus A. But in mathematics, everything has to be proved. Everything has to be defined. Everything has to be proved rigorously, and proving the existence and constructing the existence of lambda is not that simple, actually. Just like y1 plus 1 equals 2. It's mathematicians really like to be that rigorous to prove something that's really simple. It's a silly thing, but it's actually very beauty, and that's the beauty of mathematics. So the existence of uniqueness of Lebesgue measure is actually proved in the theorem called Kerosene-Dury extension theorem, and we won't go through that, but we're gonna talk some of the topics that mentioned in this theorem, and we're gonna use that as well. So the Lebesgue measure, if we use the Lebesgue measure on the interval 0, 1, that becomes a probability measure. So the next thing, once we have a probability space, the tuples, then we're gonna talk about random variables. What is a random variable? So if we look at random variable, it's also a function. It's not a number. It's a random variable, although it's called variable, but it's actually a function. Think about flipping a coin. We got a head, but we got a tail. But usually mathematicians say, okay, once you got a head, it's 1. Well, if you got a tail, then it's 0. Or we can say, okay, if you got a head, it's 1. You got a tail, it's -1, right? So why it's becoming from a letter of head, or like from the output of a sample space, head and tail, into numbers, right? So that's actually means the random variables or random vectors is actually functions, and that actually still comes down to the measure theory. And a random variable in measure theory is called a measurable map. It's a map, it's a function that maps from the omega, the sample space, to another space, S, let's say S. In our case, let's say flipping a coin, that will be from the sample space of head and tail to real numbers. So that's basically the definition of a random variable. So when the S, like I said, when the S becomes the real lines or multidimensional real lines, that will become a random vector or a random variable. And so that's the definition of random variables. Now we're gonna look at some theorems here. So here what we are looking at is if, let's say, A is a collection of subsets from the sample space S, and an A generates S, which means that so the smallest sigma field of A is actually equals to the total sigma field of the sample, the target sample sigma field S. And if we let X to be a measurable function, which is here from omega to S, if we let X to be a function of omega to S, not a measurable function, it's just a function. It's just a function. And if so, look at the condition here. If the set of omegas where X omega belongs to A, this set actually belongs to the sigma field F, and for all A in this subset collection of subsets A, then A is a measurable map from omega F to SS, the measurable space of omega F to measurable space S to sigma field S. So the proof is easy. So I listed here. So let's first look at all this possible set of A which makes X belongs to A. This set, sorry, I'm missing a curly brackets here. So X omega belongs to A, the set of omegas. If it belongs to F, then so we are looking for all the A's that satisfy this condition. So that we define we define this set to be S naught. So just know that the collection of subset A is actually is a subset of S naught. Right. So that's from here. So, but if you look at so if you take the union of set AI, which belongs to the S naught, and this is actually equal to the set of x omega. I'm missing omega here, but just a simplified notation here. So x omega, the set of omegas of x omega, belongs to union of AI. So this two is actually the same. So if a set belongs to a union of set of x belongs to AI, then the omega must belongs to the union of AI, right? So that's two equivalent sets, and that because each of those belongs to the set S naught, the AI belongs to S naught, so the set of x belongs to AI belongs to Fi. If each belongs to Fi, then the whole set, the union, belongs to F. So that indicates that the union of AI belongs to S naught. And similarly, if A belongs to S naught, and then X belongs to A complement, which is equivalent to X belongs to A complement, is in F, and that indicates that A complement belongs to S naught. So therefore, S naught is a sigma field, but it's a sigma field that contains this collection of subsets A. So the collection of subsets, so the sigma field generated by A is a subset of S naught. So that proves that X is a measurable function. That by definition of measurable map. By definition of measurable map, which means that for every set belongs to S, this condition satisfies. So for every B belongs to S, the X omega belongs to B, this set, all the omegas belongs to F. So that proves the theorem here. So the next thing I want to talk about is distribution and distribution function. Those are also we've seen that in the college level of probability courses. But I want to introduce that in a new way using measure theories. So the probability measure mu, the probability measure mu induced by a random variable x as mu a equals to p x belongs to a. For Borel set A is called the distribution of x. And fx, if we define a function fx to be p of x less than equal to x, this function f is called the distribution function of x. And the distribution function has some properties as well. First is non-decreasing. The second is limits to the infinity is 1, limits to minus infinity is 0, and then it's y continuous. So if we have a y going to the left to x, then limit of y go to x, fy equal to fx. And other properties like fx from the left side, which is the limit of y from the left side to x, which is actually equal to the probability of x less than x. And probability of x equal to x is actually fx minus fx minus, which is the limit here we've defined. Okay, so that's distribution function. The next thing is we're going to see some examples of random variables. Random variables could be many forms, and there's some very interesting forms that I want to mention. The first two is simple. So the first is if f is a measurable map, which means it's a random variable, and f is a measurable map as well. Think about it's a function from a measurable space to another measurable space, but the measurable space of x is the domain of f. Then fx is a measurable map from omega f to td. Second is if x1, x2 to xn are random variables from omega f to r Borel set Rn here. Those are n-dimensional Borel sets, and f is a Borel is a measurable map as well from the Borel space, measurable space to the one-dimensional Borel space. Then fx1 to xn is a random variable. Next two is very important random variables, and it's worth mentioning here, and it's worth paying attention here. So if x1 to xn are random variables, so let's say xn a series of random variables, the infimum of xn and supremum of the sup of xn, inf of xn, and limsup of xn, liminf of xn are all random variables. So why? So let's look at two examples here, reasoning here. So if the infimum of xn less than a, that's the omegas, the set of omegas, the infimum of xn is less than a, which means omega is which actually means is the union of xn less than a, and that belongs to sigma field f. And similarly for sup of xn less than a, which means that it's an intersection of xn less than a, and that belongs to sigma field f. So that proves that infimum and supremum are random variables. And similarly for limsup and liminf. So limsup is just a union of the intersection, union of the supremum. So the union of those sets, right? So it's a union and intersection of xn less than a, and liminf is the intersection of the union of xn less than a. So that's just intersection and union of countable sets, and each set belongs to f. So the limsup liminf also belongs to f. And that means that those limsup and liminf are also random variables. Another concept I have to mention in here is this one. So let's first so we talk about limsup liminf, and now we talk about limits of xn. And so the limit of xn exists if and only if the limsup of xn, the set limsup of xn not equal to liminf of xn, has a probability 0. So if you measure the set here, has a probability value 0. So equivalently, we say that the limsup of equal to xn, limsup of xn equal to liminf of xn is almost surely equals limsup of xn equal to liminf of xn almost surely, or almost everywhere. Which means the set of omegas of this equation has a probability 1. and usually it's called for a simpler notation, people will use a dot s, which is almost surely, which means almost surely. So and now when we talk about limits, we're gonna sometimes go out of the regular meaning of measurable space, which is excluding the infinity outside of the space. But if we take limits, that could be one of the possible outcomes, especially when we talk about stochastic processes. The process, the limits were gonna be somehow possible going to infinity. So we have to extend our measurable space that includes the plus and minus infinity. So if we extend our real line to include these two possible outcomes, and we extend our Borel sets to be generated by the sets of those forms, the open sets, half open sets, which includes the minus infinity, and infinity, and that defines the Borel set of the whole space, including infinities, and that's also a measurable space. So, uh, so yeah, that's the foundation I want to talk about here today for a probability measure, and those are very important concepts, and we're gonna use them in the future lectures. So, yeah, thank you, everyone.